Hello, everyone. Yesterday and now we are going to talk a bit about analytics, and my clicker works. So we're going to talk about applied data science. We'll go through three typical cases that you have probably already done in your companies. We're going to talk about improving detection through A/B testing. Well, I think because you're working in game dev, you are A/B testing a lot. And of course, post A/B analytics, when you have already done A/B test and you are trying to get insights from the data itself. Well, we are going to go through these three cases, and we are going to talk about typical solutions, what people usually do. From the beginning, we are going to talk about three typical use cases, typical problems that you are probably having on a daily basis, and we are going to go through typical solutions for these common problems, and we will see how they fail sometimes in very subtle ways. And of course, we're going to talk about better ways, and I will give you three tools that you can use today, well, that you can start applying today to have better solutions for these problems. A bit about me. Well, I have a lot of experience in data science, in applied data science in e-commerce. I've been doing this for 7 years. Back then, it wasn't called data science. It was called like data mining, usually. And I have some academic background. I like new papers, new approaches, if they are applicable. It means that if something is very cool and have a lot of formulas, it doesn't mean that it is useful. But if it is useful, then why don't we put it into production and use it? And yes, I have some I'm a bit of game developer myself. I had like well, I've been a level designer in a Quake 2 mission pack amateur add-on, and I've been studying C++ when I was in university, and I was thinking that I will be a game developer back then, but I ended up in data science, and yeah. Yeah. And but I ended up in data science, and after all these like 7 years, I'm returning back to game developing. Yep, and imagine my reaction when I I was making games in back then in university as a hobby. So I had like very pink tinted glasses, and then I'm going back and seeing all these like mobile games with their overuse of advertisement and so on and so on, and I'm thinking, wow, it's not like what I imagined when I was studying at university at all. Okay. Good. So, okay, that's like now onto the content itself. Again, to everyone who has missed the beginning, three cases. For each one is a problem which you have already encountered in your company probably. For each one, we are going to talk about a typical solution and what can be done better. Improving retention. Imagine we have a game. Okay, we have a game, and we see that, well, our new players are churning. Well, our players do not want to play our game for for a long time for some reason, and we want to do something about it. We want to do something. And one of the ways we can retain them, one of things we can do to keep them in games, is to give them gifts, right? For free items, that's something that is commonly done in mobile games. Yeah. But if we can give them items, but a question arises: who should receive these free items? Because we don't want, on one hand, we don't want to spoil game economy, because these items are usually received to players in exchange with real money. On the one hand, on the other, sending these gifts doesn't cost us anything, because they are in-game items. So a question: who should receive these gift items to improve retention? And a typical solution: okay, let's build a churn prediction model that will give us some scores, some prediction, and we will use this prediction to decide who should receive these gift items. Who has seen similar churn prediction based solution in their companies? Okay, that's a two. Oh, okay. Okay, who is a data scientist? Okay, who codes for a living? Who writes code? Okay, 5 hands, 6. Okay, who works in a game development company but doesn't code for a living? Okay, good. That's expected, and because of that, there won't be any technical details in the presentation. There won't be any hardcore math. There will be a solutions, why they work, and what are the situations where they are applicable. Okay, so usually when you are encountering this task, you have some churning players, you want to send gifts. The typical answer is, okay, let's build a model that will say who is going to churn. But the problem is that churn is not a well-defined thing, right? Because when you are building a model, a churn model, you want to tell it what churn is, right? So a question arises: what are we actually predicting? What is actually the score? A player wants to return tomorrow or a week, or what's the horizon? Then, okay, we have decided on the horizon of the churn. Then, what's the threshold we should use to guide our decision? Because the churn prediction, the churn score is one thing, but we have to also transform it into the actual decision to actual send items. Who should receive these gift items? What's the score? And these questions are usually hard to answer, and the typical answer is I think it just works, so let's roll with it. What happens then? Let's assume that we had built this churn prediction model, that it works, it predicts very well, it has very high accuracy, and we have some players who like these freebie items that we can engage by sending these freebies. Let's assume that we can correctly identify them and send them gifts, and they react, and they are retained. Okay, let's assume that now everything works. Okay, so we have built a churn prediction model. Let's assume that it works. Let's assume that we have used it to guide our decision who should receive these gift items. Okay, it works. But the thing is that the behavior of these users who had received these items is recorded in the data. So what happens next? Then, after some time, we will update the model. And of course, we will update it using this new data set. And this new data set will have these users who had received these gift items recently, right? And this model will see that, okay, we have some users that like freebies, but they don't churn. Well, they don't because we sent them items recently and they reacted and they hadn't left our game. And because of that, now our model assigns low churn probability to these players. Because it sees that they don't leave. And well, we don't send them items anymore. We assign them low score, etc., and everything breaks. What's the core problem of this approach? There is a disjoint between decision making and what are we trying to predict, right? Because we are trying to predict the churn probability, but this probability on its own cannot. This information is not enough to guide our decision on who should receive these gift items. Right? What's the missing piece is that this churn probability doesn't measure what we want to measure. And what I want to measure is who is the most susceptible player to these freebie items. So actually, what we want is we want to measure the change of churn probability after we send these freebie items, right? So yeah, so actually there are like prediction models which give scores and etc. And there are uplift models which are like modification of the typical prediction models. And instead of just giving a probability of some event in the future, instead they give the change of probability after we do some action. For example, the typical prediction-based model will give us the churn probability, right? But the uplift model applied to the same task will give us the change of the probability if we send this set of items. And because of that, if we use this uplift model to guide our decision, it will send items to the users who will react to these items, to these gifts the most. And because of that, it will send items to the players who are more susceptible to these gifts, so it solves our task better. So to sum up the first case, there are these uplift models which estimate gain from doing an action. They are implemented in most Python or Java machine learning packages. They are quite easy to use, and they are much more suitable than prediction-based solutions for some tasks, for example, giving items for improving retention. And well, the meta conclusion is that actually no one needs predictions, and data science is not about like making predictions or building models. That's like a misconception, very common. Data science is actually about making automated decision-making systems. Systems that that make decisions based on data and do that in an automated fashion, right? Okay, good. Second case, A/B testing new mechanics. Who had run A/B tests like in last year? Great. Okay, I'm happy to see a lot of arms. Imagine a scenario. We have a game, and we see that it underperforms in revenue for new players. Well, it happens. And we decide that, okay, let's make welcome offer pop-ups. We have a mobile game, for example, and these pop-ups will ask new players for money, essentially, and we hope that they will drive revenue and improve metrics, etc., etc., etc. We have designed 2 of them. And of course, they have some parameters. They have some variants of user like title. They have different interfaces, etc., etc. They have some parameters. So we want to first of all pick the best of 2, and second, fine-tune these parameters. Oh, by the way, who had used A/B test to fine-tune parameters of offers or game mechanics? Okay, well. I have a surprise for you. Hello. Okay. The typical solution, yes, is to run A/B tests and decide which one is the best, and probably split each group into a bunch of subgroups for each of the parameters sets, and use this large A/B test to decide what's the best of the 2 offer pop-ups, and then decide what's the best of the which is the best parameter set. The problem arises once we start the test, and it usually sounds like, okay, we have started the test. How long should we run it, first of all? Then should we stop it before the end if we see that, for example, one of the groups underperforms, and if we cross-validate our hyperparameters on the users, then we have a lot of groups, so some of them are likely to underperform immediately. Should we stop them? Should we do something about this? And the problem usually can be rephrased as, okay, we are running A/B test to make a decision what's the best offer, but we are actually spending real money to run this test, right? Good. And then after we have decided what's the best offer, what's the best set of parameters, then the question arises: is it true that this set of parameters will be the best forever? Yeah. And again, these are the hard questions. They don't have any good answers. So we can sidestep all them using multi-armed bandits. Multi-armed, okay. Who knows what I'm going to talk about now? Oh, okay. I see some arms. That's interesting. That's a set of well-known algorithms. They are widely applied, but not a game industry. Because of that, I'm here. They directly make decisions from using data from a set of pre-made decisions. They they search for the best decision from a specified predefined set, and they have some guarantees about the quality of the chosen solution. Okay, what's this algorithm or family of algorithms are about? Imagine you walk into a casino and you see a bunch of like slot machines, right? And each of them have like levers, arms that you can pull, and well, probably with some probability you get some money back. Let's imagine that you don't have to pay to like pull the lever, but each machine has its own probability to give you money and its own money distribution. You have no knowledge about the distributions of you have no prior knowledge of the parameters of the distribution, and your goal is to maximize your total profits. So to sum up, you have a bunch of machines. You can pull levers of each one. They may give you some money. You don't know what's the probability of giving you money. You don't know how much they can give you. So you have to like explore what are possible outcomes of pulling the lever on the one hand. On the other, you want to maximize your total revenue. For example, you have 3 machines. The first one gives you $5 half of the time. The second one gives you from 10 to 20, 10% of the time. But the last one gives you $1,000, but with 1% chance, right? And let's imagine that you pulled each arm twice, and you've got these outcomes, right? What will be your next pull? And based on that, you can guess that, well, B kinda looks nice, but if you actually look at the true distributions, which are unknown to you, you can see that actually it's not the case. So yeah, that's like the setting of this. That's the setting of these models. So yep, this set of algorithms provide a way to balance between exploration and exploitation, and they have some guarantees about maximizing total revenue. One of such algorithms, quite widely used, is Thompson sampling, and it's like 10 lines of code, and it works as follows. First of all, you estimate distribution for each arm, distribution of revenue that you will gain after pulling an arm. Then you draw random samples from each distribution, 1 per arm. And then you see which arm has produced the largest distribution, and you pull it. The idea is that on one hand, the arm with largest number of samples will produce the distribution with smallest variance, right? And because of that, if there is an arm which is reliable, so you have a lot of samples, and which produces a lot of like revenue on each pull, so it has high large mean, then you will pull it a lot. And on the other hand, if you have some underexplored arms, like this one, for example, then it will have like large variance, so you will sometimes pull it anyways, even if it has like very low average income on pull. And if we then translate this abstract scenario to our case, okay, finally. So if we translate this multi-arm bandits algorithm to our case, what we see is that each variant of the offer is an arm, and each user is an arm pool. So a new user comes to us, and we have to decide which offer and which set of parameters we should apply to them. right? So what we do is we estimate distribution for each arm or for each combination of parameters and offers. And then we draw samples from this distribution, and then we pull arm or we show player the offer with the largest sample. And the reward, the amount of money that that our virtual slot machines gives us, is equivalent of future money of that player that we have shown the offer. Yep, LTV. Yes. So there are some guarantees about convergence. So in A/B test, you usually spread your users evenly across all the possible scenarios, right? And if you look at this algorithm, you can see that at first, yes, it also spreads evenly users initially, but then it skews towards the best choice. And because of that, over time, it's kind of gradually converges to the best solution. And because of that, if we compare running a regular A/B test with running multi-armed bandits, you can see that they converge to the best solution in less trials. Moreover, there is a added benefit, is that you can leave. Well, you can, when you run A/B test, usually run it, then you say, okay, this one is the best, this offer or this parameter set is the best, and that's it. And you set it in stone and assume that this won't change anywhere. But usually players drift. You start buying players for new sources, etc., etc. Preference changes, and because of that, the best combination of parameters or best offer may change as well. And in case of multi-armed bandits, you can leave it running, right? You can leave it running. It will it will always pick the best solution it knows. But if at any point of time user preferences drift or something happens, they will notice that and they will change the best they will change solution they pick as well, right? They will adapt to the changes in user preferences as well, which is pretty cool. So multi-armed bandits, they are 10 lines of code drop-in replacement for A/B tests. They are easy to implement. They require some assumptions about the setting, but in most cases and in the provided one, they are met. And the meta conclusion is that machine learning models, and all models, they have some assumptions behind them, right? You cannot just take a model, apply it to any scenario and expect it to work. And usually no one checks these assumptions for some reason, but if you do, and if you apply the right models to the right scenario, then of course they will work. And yes, you shouldn't cross-validate hyperparameters on users using A/B tests. So that's the answer to 5 people who raised their arms because first of all, that's inefficient, and second, there are better solutions to this problem. Multi-armed bandits. Third case. Imagine that we had run A/B test. excuse me. Imagine we are releasing an update, right? We have patched some crashes, we have some optimizations, and we of course changed some gameplay things, and we expect them to improve our monetization. Well, and of course we don't want to roll out these changes on all of our players, so we chose a half, and we rolled out these changes on this half of the players. Well, essentially we are running A/B test, and 1 week had passed, and now we have a question: does these changes? Now we have a question whether these gameplay changes, for example, are actually giving us more money, and well, what should we do about it? We have an update. We have introduced some changes. We have run an A/B test. A week had passed. Now we have to decide what to do now, and the typical solution is to look at the dashboard. Well, I think everyone has some sort of dashboard, and for example, it says plus 10% average revenue per user for which we had our update. A question: should we roll out this update on 100% of the players? No. First of all, let's look at first of all, average revenue per user is like a bit tricky metric, and imagine that our dashboards looks like this. Yes, these are days. We have 7 days. That's the actual numbers, right? And what our intuition says: okay, let's add up all these numbers, and we get the total average revenue per user for this group, right? And no, yeah. And if we divide one total by the other total, we get this total lift. But actually, it's not the case, because average revenue per user is not an additive metric. What I mean by this is you cannot just take average revenue per user for 1 day, for a second, for a third, and for each of the 7 days, add them up, and get a average revenue per user for the whole week. Why? Because let's look at the example. We have 3 days, right? During the first day, player A left $1, player B left $0, but he had played the game. The other 3 hasn't played. During the second day, B didn't pay as well, but during the third day, B had left $1, and we also had players D and E, which also left $1 each. If we calculate average revenue per user for each day, what we get? For the first day, 50 cents per player, second day 20 cents per player, and third day 60 cents per player. If we add them up, right, we get $1.30. But if we now calculate average revenue per user the right way, what we get? Our total revenue is $5, right? We have 5 players, and if we divide 5 by 5, we get $1. That's the right way to calculate average revenue per user, and this one we may get if we make a mistake and we start adding daily average revenue per users. I think it's a bit obvious, but I sometimes see it, and using this may give us wrong decisions. It may give us wrong metrics, especially in cases when the distribution of users across time is not uniform. For example, we have more users on the weekends, and in these cases, the discrepancy between this number and this one number will be very high, and we may end up like choosing the wrong group or something. Okay, back to our imaginary scenario. Let's now say that we had recalculated average revenue per user in the proper way, in the right way, and we had now we have 5% lift. Should we roll out our update on the 100% of the users? The answer is no. Again, why? Because, well, 5%, but can we attribute this 5% to the randomness? Because maybe it's just some noise, and actually there are no the actual lift is negative, for example. And also there may be some confounding things, confounding effects. For example, if you break Android, to remind you, we tried to optimize for Android, and we also fixed some crashes on iOS. And let's imagine, because of that, we may end up with more iOS players and less Android players. And iOS players usually pay more, and because of that, we may see this metric as well. But actually, we haven't changed anything in terms of gameplay quality. But yeah, as I said, this 5% also can be attributed to pure randomness, and that's this thing, this problem we can tackle now. It can be tackled using confidence intervals. Instead of having one metric, we can use metric and some upper and lower thresholds for each one. And most of metrics we want to use do not have explicit formula for confidence intervals. For example, average share rate per user, I think, yes, it does have explicit formulas. But if you, for example, look at how long player stays on level 1 in our game, or how much money does player leaves on average between level 1 and level 10 in our game, and other very fine-grained metrics that we sometimes use, they don't have explicit formulas. What's the solution? Is, well, there is a Bootstrap. Bootstrap is an algorithm that can calculate confidence intervals for any player-based metric. And it looks like this. First step is we calculate an array of our metrics, where each number is the excuse me. The first step of this Bootstrap algorithm is we calculate X, which is an array of player-wise metrics, right? And the second step is that we first of all we resample X and compute the resampled average. And we repeat this many times. And after that, we have a bunch of different averages. And then we can take and compute percentiles of these averages. And that's it. We compute the median, or the 50% percentile of these averages. That's the average value of our metric. And 5 and 95% are the lower and upper confidence intervals.
I'm sorry, we're just taking time off the next session. Can we please move to the...
Okay, good. Conclusion. The Bootstrap is 10 lines of code. and it is easy to implement. There is some intuition why it works and why it works and how it can produce the confidence intervals. And to sum up, yeah, a bit of personal speculation. Okay. So to sum up, what we've learned today. First of all, belief modeling, a better alternative to just predicting things. In second case, we have learned multi-armed bandits, a better alternative to running A/B tests. And in third case, we almost learned bootstrap technique for confidence intervals. And I have like I have some personal pet theories about why do we see why data science hasn't been widely adopted in gaming industry, but well, we don't have a lot of time to talk about them. But well, you may ask me, and of course, it will make a great discussion points. Yep, that's it.
Thank you very much. Please, a round of applause to the speaker.